October 14th, 1947. A bright orange aircraft hung beneath the belly of a B-29 bomber at 20,000 feet over the Mojave Desert. Inside that aircraft sat a 24-year-old test pilot named Chuck Yeager, nursing 2 broken ribs he hadn't told anyone about. In a few minutes, he would attempt something that many scientists believed was physically impossible. He was going to try to fly faster than the speed of sound, and if the theorists were right, the moment he crossed that invisible barrier, his aircraft would be torn apart by forces no human had ever survived. This is the story of the reaction Motors XLR11 rocket engine, and how a piece of technology smaller than a refrigerator changed everything we thought we knew about flight. Along the way, we'll encounter frustrated engineers, skeptical generals, exploding test stands, and a barrier that wasn't really a barrier at all. So let's begin. But first, why did everyone think the sound barrier would kill you? See, by the mid-1940s, aviation had a problem. Propeller-driven aircraft had pushed up against a ceiling that nobody knew how to break through. As planes flew faster, approaching the speed of sound, strange things started happening. Control surfaces stopped working, wings began to shake violently. Some aircraft simply disintegrated in midair. Pilots who survived these encounters came back with terrifying stories of invisible walls and aircraft that seemed possessed. The military had a term for it. They called it compressibility. What was actually happening was this. As an aircraft approaches the speed of sound, the air in front of it can't get out of the way fast enough. It starts piling up, creating shock waves that play havoc with aerodynamics. The faster you go, the worse it gets. And at exactly Mach 1, 0.767 miles per hour at sea level, theories suggested you would hit a wall of compressed air that no aircraft could survive. Now, I should mention, not everyone bought this theory. Some engineers suspected the problem wasn't the speed of sound itself, but rather the aircraft designs that were trying to reach it. Propeller planes with their thick wings and blunt noses were simply the wrong tool for the job. The question was, what was the right tool? And that's where the story gets interesting. Because while American aeronautical engineers were scratching their heads about transonic flight, a completely different group of engineers had already been solving a related problem. They were building rockets. The Reaction Motors Company was founded in 1941 by 4 members of the American Rocket Society. These weren't military contractors or aerospace giants. They were rocket enthusiasts, tinkerers, the kind of people who spent their weekends in the New Jersey Pine Barrens testing experimental motors that had an unfortunate tendency to explode. Their names were Lovell Lawrence Jr., John Shesta, James Wild, and Hugh Franklin Pierce. And their timing was extraordinary, because just as they were getting their company off the ground, the United States military suddenly became very interested in rocket propulsion. The thing about rockets is that they don't care about air. A jet engine needs to suck in oxygen to burn its fuel. That means at high altitudes, where the air is thin, jet engines lose power. And at the edge of space, they stop working entirely. But a rocket carries its own oxidizer. It works just as well at 50,000 feet as it does at sea level. Better, actually, because there's less air resistance. The military's interest wasn't in breaking the sound barrier, not initially. They wanted high-altitude interceptors, aircraft that could climb fast enough to catch enemy bombers before they dropped their payloads. And for that mission, rockets had obvious advantages. But building a reliable, controllable rocket engine turned out to be enormously difficult. The problem wasn't generating thrust. That was relatively straightforward. Mix fuel and oxidizer in a combustion chamber, ignite it, and you get thrust. The problem was not blowing yourself up in the process. Early rocket engines had a nasty habit of exploding. The combustion temperatures were extreme, often exceeding 4,000 degrees Fahrenheit. Cooling was primitive, and the fuels themselves were frequently toxic, corrosive, or hypergolic, meaning they ignited spontaneously on contact with the oxidizer. One wrong move, and you had a very expensive fireball. Reaction motors spent years working on these problems. They experimented with different fuel combinations, different injector designs, different cooling systems, and slowly, painfully, they figured out how to build a rocket engine that wouldn't kill its operators. By 1943, they had a working prototype that used liquid oxygen and ethyl alcohol as propellants. It was designated the XLR11. I want you to understand how revolutionary this engine was. The XLR11 produced 6,000 pounds of thrust from a package that weighed about 210 pounds dry. That's a thrust-to-weight ratio that jet engines of the era couldn't come close to matching. More importantly, it was controllable. The engine had 4 separate combustion chambers, each producing 1,500 pounds of thrust. The pilot could ignite them individually, giving him precise control over his power output. He could run on 1 chamber for cruise, 2 for climb, 4 for maximum performance. This was completely different from the rockets that had come before, which were essentially controlled explosions. The XLR-11 was a precision instrument. But here's the thing about the XLR-11 that really mattered. It worked at any altitude and any airspeed. A jet engine's performance is tied to its forward motion. The faster you go, the more air you ram into the intake, the more power you can generate, up to a point. But approach the speed of sound, and shock waves start forming in the intake. The airflow becomes chaotic. Power drops off. The XLR-11 didn't have this problem. It didn't care about the air outside. It didn't care about shock waves. It would give you 6,000 pounds of thrust whether you were at Mach 0.5 or Mach 1.5 or sitting still on a test stand. This made it the perfect engine for exploring the transonic regime, that mysterious zone where aircraft had been dying for years. The Army Air Forces figured this out in 1944. They contracted with Bell Aircraft to build an experimental plane specifically designed to break the sound barrier. It would be called the X-1, and it would be powered by the XLR-11. Now, the X-1 itself was a remarkable piece of engineering. Bell's designers studied the one thing they knew could go supersonic without falling apart, a .50 caliber bullet. The X-1's fuselage was literally shaped like a bullet, with a pointed nose and a cylindrical body. Its wings were thin and straight, designed to minimize the shockwave problems that had plagued earlier aircraft. The horizontal stabilizer was adjustable in flight, allowing the pilot to compensate for the shifting center of pressure that occurred at transonic speeds. But all of that clever aerodynamics would have been useless without an engine that could actually push the aircraft past Mach 1, and that's where the XLR-11 came in. The engine was installed in the tail of the X-1, with 4 exhaust nozzles protruding from the back. The fuel and oxidizer were stored in tanks in the fuselage, giving the aircraft about 2.5 minutes of powered flight. That doesn't sound like much, but it was enough. Because the X-1 wasn't taking off from a runway, it was being dropped from a B-29 bomber at high altitude, already moving at 200 miles per hour. Every second of that 2.5 minutes counted. The test program began in 1946 at Muroc Army Airfield in the Mojave Desert. The early flights were glide tests with no fuel in the tanks, just to verify that the X-1 could fly at all. Then came powered flights at progressively higher speeds, Mach 0.7, Mach 0.8, Mach 0.9. Each flight pushed a little further into the unknown, and with each flight the engineers learned something new about transonic aerodynamics. The pilot for most of these tests was a civilian named Chalmers Goodlin. He was good, but he was also careful. Too careful, in the opinion of some. Goodlin wanted more money and more safety guarantees before attempting the sound barrier itself. Bell Aircraft was willing to negotiate. The Army Air Forces was not. They were tired of delays. In the summer of 1947, they took over the program and assigned their own pilot. His name was Captain Charles E. Yeager. Yeager was 24 years old, a combat veteran with 11 confirmed kills in the European theater. He had once shot down a German jet one of the Me-262s that were supposed to be unbeatable by catching it during takeoff when it was slow and vulnerable. He was exactly the kind of pilot the X-1 needed. Aggressive, skilled, and not particularly worried about dying. He also had a natural feel for aircraft that bordered on supernatural. Other pilots described it as an instinct, an ability to sense what an airplane was about to do before it did it. This would prove essential in the weeks to come. Yeager made his first powered flight in the X-1 on August 29, 1947. Over the next 6 weeks, he would make 8 more, pushing steadily toward Mach 1. Each flight revealed new challenges. At Mach point 94, the controls became so sensitive that the slightest input sent the aircraft pitching wildly. The X-1's engineers installed a new stabilizer mechanism that gave Yeager more authority at high speed. At Mach point 97, severe buffeting shook the aircraft, but it passed. At Mach point 99, the Mach meter on the instrument panel began to fluctuate strangely, bouncing between readings as if it couldn't decide how fast they were going. And then, on October 14, 1947, they went for Mach 1. If you've made it this far, you're probably into this kind of stuff. Quick question, where are you watching from? Drop it in the comments. And hey, subscribe if you haven't. We do this every week. All right, back to the Mojave. The morning of the flight, Yeager almost didn't go up. 2 nights earlier, he had been riding horses with his wife Glennis near their quarters at Mach. The horse threw him. He hit the ground hard and cracked 2 ribs on his right side. He knew that if he reported the injury, he would be grounded. The flight would be postponed, maybe given to another pilot. So he said nothing. He found a local veterinarian who agreed to tape his ribs without asking too many questions. He told his crew chief, Jack Ridley, because he needed help with one specific problem. The X-1's cockpit door had a heavy latch that required the pilot to reach across his body with his right arm and pull hard to secure it. With broken ribs, Yeager couldn't do it. Ridley improvised a solution. He cut 10 inches off a broomstick and gave it to Yeager as a lever to close the door. That morning, Yeager climbed into the bomb bay of the B-29, shimmied down a ladder into the X-1 hanging below, and pulled the door shut with a broomstick. The B-29 climbed to 20,000 feet. At 10:18 in the morning, they dropped the X-1 into the clear desert air. Yeager ignited the first chamber of the XLR11, then the second, then the third and fourth. 6,000 pounds of thrust shoved him back in his seat as the X-1 accelerated. He climbed and accelerated simultaneously, trading altitude for speed, the XLR-11 screaming behind him. Mach point 88, point 92, point 96. The Mach meter needle crept upward, entered the zone where it had fluctuated wildly on previous flights. And then, at 43,000 feet above the Mojave Desert, something remarkable happened. The buffeting stopped. The Mach meter needle jumped off the scale and fell back to zero, unable to measure the aircraft's speed. The air became smooth. The controls felt normal. Chuck Yeager had just become the first human being to fly faster than the speed of sound in level flight. On the ground, observers heard something they had never heard before. A double crack like a thunderclap rolling across the desert floor. It was the sonic boom, the sound of the shock wave from the X-1 reaching the Earth. The sound barrier hadn't been a wall at all, it was a door, and the XLR-11 had just kicked it open. Now, I want to stop here and talk about what made this possible. Because it wasn't just Yeager's courage, though that was certainly a factor, and it wasn't just Bell's clever aerodynamics, though those mattered too. What made the X-1 program succeed was the XLR-11 engine, and specifically the qualities that made it different from every other power plant available at the time. Consider the alternatives. The jet engines of 1947 were getting better every year, but they were still fundamentally limited by their air-breathing nature. At high altitudes, they lost power. At transonic speeds, they suffered from intake instabilities that could cause compressor stalls and flameouts, and they couldn't be throttled quickly. A jet engine takes time to spool up or down, which made precise speed control difficult. The XLR11 had none of these problems. It produced consistent thrust regardless of altitude or airspeed. Its 4 independent chambers allowed the pilot to add or subtract power in precise 1,500-pound increments, and it responded instantly to throttle inputs. In the transonic regime, where small changes in speed could produce dramatic changes in aircraft behavior, this level of control was invaluable. But the XLR11's advantages went beyond pure performance. The engine was also remarkably reliable, at least by rocket standards. Reaction motors had spent years solving the problems that plagued early rocket engines: the injector failures, the cooling system breakdowns, the combustion instabilities that could cause an engine to tear itself apart. The XLR11 wasn't perfect. It could still fail, but it failed rarely enough that pilots were willing to trust their lives to it. Think about that for a moment. In 1947, rocket engines were considered inherently dangerous. The V-2 missiles that Germany had rained on London just 2 years earlier had a failure rate that would have been unacceptable in any other weapon system. And yet here were American test pilots climbing into aircraft powered by rocket engines, doing it repeatedly and surviving. That's a testament to the engineering work that reaction motors had done. They had tamed the rocket. Not completely, but enough. The XLR11 would go on to power some of the most important experimental aircraft of the post-war era. The X-1 flew until 1958, setting speed and altitude records that pushed the boundaries of human achievement. Its successors, the X-1A, X-1B, and X-1D, all used upgraded versions of the XLR11. The Douglas D-558-2 Skyrocket, which became the first aircraft to exceed Mach 2, was powered by the same engine. So was the Bell X-1E, which tested new wing designs for supersonic aircraft. In total, the XLR11 and its variants flew in research aircraft for over 15 years, generating data that shaped every jet fighter, bomber, and airliner that followed. But perhaps the most important thing the XLR11 did was prove that the sound barrier was a myth. For years, aeronautical engineers had debated whether supersonic flight was possible. Some believed that the forces at Mach 1 would always exceed any aircraft's structural limits. The XLR11 and the X-1 proved them wrong. The barrier existed, but it was an engineering challenge, not a physical law. With the right design and the right engine, it could be overcome. That insight changed aviation forever. The story doesn't end there, of course. The quest for speed continued. In the years after Yeager's flight, aircraft pushed to Mach 2, then Mach 3, then beyond. The X-15, powered by a much larger rocket engine, would eventually reach Mach 6.7, so fast that its pilots qualified for astronaut wings because they flew above 50 miles altitude. And all of that progress traces back to a small company in New Jersey, 4 rocket enthusiasts who believed they could build something better, and an engine that weighed 210 pounds and changed the world. And what of the men who made it possible? James Wilde, who had designed the regeneratively cooled combustion chamber that made the XLR11 practical, died young in 1953 at just 40 years old. He never saw the full flowering of the technology he helped create. Lovell Lawrence Jr. went on to lead reaction motors through the 50s, overseeing the development of larger and more powerful rocket engines, including the engine that would power the X-15. The company was eventually absorbed by Thiokol Chemical Corporation in 1958, its technology and expertise distributed throughout the American aerospace industry. As for Chuck Yeager, he continued flying experimental aircraft for years, becoming arguably the most famous test pilot in history. He survived crashes, ejections, and close calls that would have killed lesser pilots. He retired from the Air Force as a brigadier general in 1975. As of this recording, he lived to be 97 years old, long enough to see the aircraft he tested become historical relics in museums and the barrier he broke become a footnote in aviation history. The thing about the XLR11 that strikes me most is how simple its genius was. Everyone was trying to make better jet engines, more powerful, more efficient, more capable. Reaction motors asked a different question. What if we don't use air at all? What if we carry our own oxidizer, ignore the atmosphere entirely, and build an engine that works the same whether you're at sea level or the edge of space? It sounds obvious in retrospect. Most great ideas do. But someone had to think of it first. Someone had to prove it could work. And someone had to trust their life to it. On October 14, 1947, a 24-year-old pilot with 2 broken ribs and a broomstick in his pocket trusted his life to a 210-pound engine built by 4 rocket enthusiasts from New Jersey. And when he lit those 4 chambers and pushed past Mach 1, he proved that the impossible was just another engineering problem waiting to be solved. And that is the story of the Reaction Motors XLR11. Subscribe if you want more, and let me know in the comments, had you ever heard of this engine before? Take care, and I'll see you in the next one.